This is Mr. Beck Does Your Homework. We are up to questions 12, 13, and 14. Parts 1 of 3, 2 of 3, and 3 of 3. Question 12 says, a uniform rod supported and pivoted at its midpoint, that's important, but initially at rest, has a mass of 64 grams, watch out for grams, and length 6 centimeters. A piece of clay with mass 23 grams, again grams, and a velocity of 2.9 meters per second hits the very top of the rod, it gets stuck, and causes the clay rod system to spin about the pivot point O at the center of the rod in a horizontal plane. Viewed from above, the scheme is such and such. And it's viewed from above so that you know that you don't have to worry about the gravity accelerating it down and around and stuff. With respect to the pivot point O, that point in the middle, what is the magnitude of the initial angular momentum of the clay rod system? After the collisions, the clay rod system has an angular velocity, omega, about the pivot. But beforehand, it's just really this that's moving. So, the initial angular momentum, as we've learned in a couple other problems, has to do with the mass times its velocity times its radius. This is for a mass that's moving in a straight line. We will have mvr in order to give us the angular momentum of that mass. So now you're going to plug in, careful of your mass. Mine is 23 grams, so that is going to be a mass of 0.023. My velocity here is 2.9 meters per second. And my radius is, let's see, 6 centimeters here, but divided by 2, so I'm going to have 3 centimeters. And if I know my conversions, I know that's 0.03. So that is going to be my MVR for that. Now question 13 asks, with respect to the pivot point O, what is the final moment of inertia of the clay rod system? So here I'm looking for the moment of inertia, and this is going to be the moment of inertia of the rod plus the moment of inertia of the clay. I can just add them together. The moment of inertia of the rod, if you look that up, you will find it is 1/12 ml squared. So that is going to be 1/12, because it's a rod spinning around its center, times the mass of the rod, times the length squared. And to that I'm going to add the the moment of inertia of that mass, this clay that's going to be moving in a circle now. And anything that is just a point mass that's moving in a circle, I can say is going to be the mass times its radius squared. So I'm going to add to that the mass of the clay times the radius squared. So I've got 1/12 ml squared plus mr squared. So in my case, that's going to be 1/12 of the mass of the rod, which is 64 grams. So that's going to be 0.064, that's 64 grams, times L squared, and L is 6 centimeters, so that's 0.06 squared, plus mr squared, that's the mass of the clay, which is 23 grams, 0.023 kilograms, times r squared, and that's 0.03 squared. So when I do all of that, I will get myself the moment of inertia of the clay rod system. Now for question 14 says, what is the final angular speed, omega final, omega f, of the clay rod system? Well, here it's a conservation of momentum problem. So initially the clay had some angular momentum, and afterwards the clay rod system is going to have some angular momentum. So I already have my angular momentum of the clay moving by itself, but now I need the angular momentum of the whole system. The angular momentum of the system is going to equal the moment of inertia of the system times omega. That's the omega I'm looking for. So L would equal I omega, just like P would equal mv. So L is like P, I is like m, and omega is like v. I already know L from earlier. I know I from right here, so I'm just looking for omega, and that should be pretty simple to solve for.